Hey, today we're going to talk about valence electrons, folks, and what that means, what they are, how can we use electron configuration to figure out some of this stuff, and what you're going to need to know for future quizzes and tests. So, let's get started here. Quick review, let's write the electron configurations for these atoms. So what I'm going to have you do is make sure you pull out your periodic table. You're going to need that for the entire presentation here. Just remember, have something that looks like that. You got the purple one that I gave you. Make sure you have that out. You're going to want that periodic table, and I'm going to go back and forth periodically to those things. So make sure you have it. So electron configuration for lithium. When you look at the periodic table, lithium is number 3, which means for us it has a total of 3 electrons, which is good to know. Electron number 1 and 2 are represented by hydrogen and helium on the periodic table. And they're in the first row, so that tells us they're in the first energy level. And remember, the first 2 up and down columns, which helium is technically part of, are considered s orbital electrons. So we write an S. And then there's a total of 2 of them, electron number 1 and electron number 2. So that's what we'd use for our power. And now lithium's got one more electron, number 3. And when you look at the periodic table, it's in the second row, so that tells us it's in the second energy level. And it's in the first column, and everything in the first 2 columns are s orbitals. But here there's only 1, so we're going to have a power of 1 on the s. Do the same sort of thing for potassium. Potassium is K, number 19. First 2 electrons are hydrogen and helium, so that would be 1s2. Next electrons, electron 3, 4, 5, 6, 7, 8, 9, and 10. If you look at your periodic table, those are all in the second row. Okay, but electron 3 and 4 are part of the s orbital, first 2 columns. So there's 2 of those. And then electron 5 through 10, they're still in the second row, second orbital, so we put a number 2. But now they're in that next block, which we call p orbitals. And there's a total of 6 of them, 5, 6, 7, 8, 9, and 10. So we put a power of 6 there. Keep going. Electron 11 and 12 on your periodic table are represented by number 11 and 12. And they're now in the third row. They're in the first 2 columns, so that would be an s orbital. And there's a total of 2 of them, so power of 2. And then electron 13 through 18, still in the third row, so third energy level. They are a p orbital, because they're in the next block over, and there's a total of 6 of them. So put a 6 as your power. And then for the last electron, number 19 for K, now in the 4th row, so 4th energy level. It's in the first 2 columns, so that'd be an s orbital, and we put a power of 1, because there's only 1 of them. So just a quick refresher, remember that's proficiency 5A. It turns out that this is going to make figuring out what a valence electron is really, really, really simple. So, first off, brief definition, valence electrons, it's just the electrons in the outermost energy level. So we want to be careful here. When you start getting big, big atoms, the electrons don't always fill up on the inner energy levels first. There's some overlap there between those different orbitals. So sometimes we're going to have a weird thing happen, but we're just looking at the outermost energy levels. And if you think of electron configuration, you know, looking back at this one here, you would figure that out by just looking for the biggest number in front. So for lithium, the outermost energy level 2. And you would just count up the powers, and that tells you how many valence electrons you have. For potassium, energy level 4 is the biggest energy level. So you would be able to figure that out just by looking at those powers. So we did an example here. Here's boron. Boron is number 5 on the periodic table. So a neutral atom of boron has 5 electrons. And when you look at the electron configuration, I've done this one for you, notice when you add up all the powers, 2 plus 2 plus 1, that should always equal your number of valence electrons. So boron has 5. Well, if I were to ask you where is the outermost energy level, all you have to do is you look for the biggest numbers out front. So boron's in the second row, so we know it has a total of 2 energy levels. So any of the electrons in that second energy level, that's farther away than the first energy level. So these would be your valence electrons. So it's really pretty easy. So again, the definition, valence electrons, just which electrons are farthest away from the nucleus and what energy level are they in. And that's what you do. Look at your electron configuration. Okay, so let's do this for sulfur now. I'm going to recommend try pausing this and then try to figure out the electron configuration for sulfur. And when you think you have it, unpause the video and I'll show you what the electron configuration actually should be. It'd be a way to check your work. So practice this real quick. Pause right now and then come back in a little bit. Okay, you think you got it? Let's see what you got. This should be what you have for sulfur. 1s2, 2s2, 2p6, 3s2, and 3p4. If you're struggling on this, if you don't remember how to do this, my recommendation is go to the class Moodle site. We have a lot of little videos on Proficiency 5A. That's what this is here. This is Proficiency 5A. You need to do some review, and I would recommend you do that before you continue on, because if you don't know how to do these electron configurations, valence electrons are going to be much, much harder for you. So anyway, here's sulfur. Which of these electrons would be considered your valence? Remember, the definition of valence is the electrons in the outermost energy level. We're not looking at individual orbitals, we're looking at entire energy levels. And again, to figure that out, real easy. You just look at your electron configuration and you look, oh, these are the biggest numbers that represent an energy level, so these must be my valence electrons. And sure enough, that's correct. So here's how we use valence electrons and why it's useful. It turns out in nature, atoms like to form this rule called the octet rule. And it basically just means every atom wants to have 8 valence electrons. So when you look at the outermost energy level, the biggest energy level, atoms want to make sure they have 8 valence electrons, if they can help it. This isn't always going to be able to happen, but if they can help it, that's what they're going to do. There's a couple reasons for that. One, they want to get their electron configuration to look just like the nearest noble gas. So when you're looking on your periodic tables, everybody do that right now. The noble gases are the farthest column to the right, column number 18. Got helium at the top and octium at the bottom, with radon right above that. Turns out that all of the noble gases have perfectly filled energy levels, and that just makes atoms really, really happy. There's this law of laziness I'm going to talk about here, and you may have heard me talk about it briefly in class. It basically just says atoms always want to do the least amount of work possible. Well, it turns out that if your energy levels are full, meaning you don't have any empty gaps in any of your orbitals, they're all filled with electrons. What that means for an atom is it isn't easily able to have a chemical reaction. And if you think of a chemical reaction as doing work, if possible, atoms want to avoid that. They're lazy. So if an atom can get its electron configuration like a noble gas, all of its energy levels will be full, and it's going to react less. It'll have lower energy, is what we in chemistry say. So, obviously, there's some exceptions. There's almost always exceptions to some of this stuff. The 4 exceptions you need to know are hydrogen, lithium, beryllium, and boron. And if you look at your periodic tables, if you look at those, hydrogen, helium, lithium, beryllium, they're all the first 4 elements. Well, the reason that they want to only have 2 is because they're closest to helium. Helium is the nearest noble gas for those 4 elements. Well, think about that. Why would this make them only want to have 2 valence electrons? Think about what the electron configuration is for helium. So see if you can do that right now. I would recommend you pause it, and then I'll be right back. So draw the electron configuration for helium. Okay, did you get it? And this is what you should have. 1s2 is the electron configuration for helium. And that is really important because when you, again, count the powers, that tells you how many total electrons helium has. Helium only has 2. So since hydrogen and lithium and beryllium and boron are all closest to helium, they want to get their electron configuration like helium, because helium is the nearest noble gas, and helium only has 2 electrons. So they also only want to have 2 electrons. So let's do some practice here. Atoms will want to gain or lose electrons to become like the nearest noble gas. I just said that a little bit ago. Law of laziness is going to kick in here. Okay, remember atoms, the law of laziness says atoms will want to do the least amount of work possible. You know, atoms, if they could, they just, kick up their feet on a lazy boy, sit back, watch football all day, eat chips, play video games, whatever you think of when you're just being lazy, just relaxing, doing nothing, no work. Atoms want to do that too. But for them, that has to deal with gaining or losing electrons. So the reason atoms want to get to the nearest noble gas is because they want to do the least amount of work, and the nearest noble gas is doing the least amount of work. So they're going to either gain or lose electrons, okay? But they're only going to do whichever one involves the fewest number of electrons, okay? So they're going to gain or lose depending on which requires them to gain or lose the least number of electrons. The more electrons you have to move, either taking them in or giving them away, that's more work. So they want to do the least amount possible. So if we do that, then remember electrons have a negative charge. So if you're gaining electrons, you're gaining negative charges, your atom's going to become negatively charged. If you're losing electrons, you're losing negative charges, and you still have a bunch of positives left over, so you're going to become more positive. So when atoms do this, they become ions. Remember, we talked about real quickly, an ion is just any atom that has a charge. Well, this is how they get like that. They're gaining or losing electrons so they can become like the nearest noble gas. So some quick practice. Write the electron configuration of beryllium. To become like the noble gas, what is it going to do? What are its options? So I'm going to do that let you do that real quick. So pause the video, write the electron configuration of beryllium, and then we'll be right back. Okay, here's what you should have for beryllium. Okay, so beryllium, nearest noble gas, is helium. Okay, its options though are this. It could gain 6 electrons to become like neon, and this is the electron configuration for neon. Or if it lost 2 electrons, it'd become like helium. Well, which is easier? Which involves the least number of electrons being moved? That's the least amount of work. And so beryllium's looking at this and says, well, I could either gain 6 electrons or I can lose 2. Well, if I'm only shifting 2 electrons around, that's a lot less work than trying to gain 6 electrons. So beryllium's going to try to lose 2. And when it does that, it becomes like helium. Okay? So always just kind of look, which is the fewest number of electrons being moved? And when you're looking at your periodic table, all that means is which one has the fewest number of elements or boxes in between that element and the nearest noble gas. So let's think about this now. Beryllium loses 2 electrons, and each electron has a negative charge. Okay? So how many charges will it be positive, will it be negative, and how much for beryllium? Well, if you lose 2 negative charges, that means you're going to become +2. So if we look at this, beryllium's number 4, atomic number 4. Remember, the atomic number tells you how many protons you have. So since beryllium's atomic number 4, you got 4 protons. And it now only has 2 electrons, where before it had 4. So if you have 4 positives, 2 negatives, you're going to have a +2 charge overall. So here's some practice. See what you can do. When you're done, pause this. When you're
We
done,
have the following students.
look at your
To
answers.
the Blue House, please. Sakna, Nip, and Caitlin Knoll. Also, Kira Mickelson, Sarah Aschenbach, and Colin Deloney. To the Blue House, please. Colin Deloney,